Hi everyone, I'm Amir Zamir. Today in the talk, I would like to talk about 3D representations, especially graph-based representations that enable integrating 3D and semantics, how to extract such information from images, and how to use the extracted information for downstream goals like for robots. So first about representations. We have a number of options for representing 3D content, like volumetric representations, surface-based representations, point cloud, and so on. And similarly, we have a number of options for representing semantics. For instance, given an image, we can attach a label to the entire image, like there's a chair here, or you can put a bounding box around the chair, or you can segment the chair out, or you can put a natural language caption that describes the content of the image, or more recently there are like graph-based representations like scene graph that besides including what elements are in the scene, they also incorporate the relationship between them. So all of these represent the same semantic content in just different ways. So despite the fact that we have different options for either 3D and semantics, there's usually a divide between them because there are not many options for representations that integrate the two in a unified way. And 3D scene graph that we have been working on is a step in this direction. So what is 3D scene graph? So it's basically a layered graphical representations of an entire building, and it includes both 3D and semantics. So here it's shown for an example building. This is using existing industrial 3D sensors that give you building-wide meshes and registered images on the mesh. So you represent the entire building with a node, and then within the building there are spaces. So each of the spaces are represented with a node as well. These are rooms basically, and then within each room there are a number of objects. So each room is then decomposed into the objects. Each object is represented with a node, and then there are images in the building, and each of those are represented with a node as well. Each of these nodes have attributes. For instance, the field of view, modality, pose, the intrinsic and extrinsics of the images, the attributes of the node, and for objects, what class the object belongs to, what size it is, and so on and so forth. So all these nodes have some attributes specific to their category. And then there are relationship between nodes. They are basically edges of the graph. So this is pretty informative. Think about the concept of, for instance, occlusion. Occlusion can be represented with a higher order edge in this graph, because occlusion is basically the relationship between two objects from a particular camera viewpoint. So you can think of representing occlusion as an object, camera, object, edge. So if you have a representation like 3D scene graph for an entire building, one could query the graph for such relationships and retrieve where occlusion occurs in this building. And there similarly, you can represent many other forms of information based on relationship between elements in the graph. For instance, let's say relative volume. Is space A bigger than space B or not? This is just simply a graph in the edge. Or whether two objects belong to the same room or not. So that's a relation between object, space, and an object. That's a higher order edge as well. So this type of information is not something that is convenient to represent using conventional representations. Let's say if you have depth or surface normals or object bounding boxes, because many of these things are just defined when you incorporate the relationship between different elements. It's not about individual elements. That's why graph-like representations, we believe, are powerful here. So now this was about the structure of 3D scene graph. How to extract the 3D scene graph for building when you have some raw data for building. Like I said, the data that we want to do this on is the output of existing industrial sensors that are available in the market. There are plenty of options for them. So they give you a building-wide mesh plus images that are captured in the building. So they are registered on the mesh. So you get a set of equirectangular images and their camera parameters and the building-wide mesh. So how are we going to extract the 3D scene graph for such a building? So clearly manual labeling is infeasible. You would have to segment the entire mesh, segment the objects, attach a label to them, put in their attribute and sizes and so on. It's clearly a very infeasible manual annotation job. So the rest of this paper was about an automated pipeline for extracting 3D scene graph by using existing semantic detectors without having to do everything manually. So I'm not going to get into details of it. I'll just convey the idea, and I let you see the paper for the details. The idea was that, like I said, the output of the sensors is a set of images and a building-wide mesh, and these images are registered in the mesh. So we run existing semantic detectors like mask CNN on these images and get a set of coarse object detections. So these are not perfect because MaskR CNN is not perfect, COCO is not perfect, and also the registration of the images on the mesh are not also perfect. So we need to use a number of robustification mechanisms to improve it. So we use two mechanisms. One of them is framing, and the other one is multi-view consistency. Framing is based on the fact that when you want to detect an object in the image, where the object is placed in the image matters. Like usually if you put the object in the center of the image and zoom around it just enough, not too much, not too little, you have a higher chance of detecting that object using existing semantic detectors versus when the object is on the side of the image and then partially occluded and so on. That probably says something about the biases of the data sets that we have. But basically framing is the process that selects the image that you feed into MaskR CNN in a way that it maximizes the performance of it. Since the data is in the form of equirectangulars, you can basically find the frame and then it's up to you basically to find the frame to maximize the performance of MaskR CNN. So that's the first step that we did, framing. And second one is multi-view consistency. That is based on the fact that all the objects that you see in the mesh are visible from multiple panoramas. So if you have the semantic detections in multiple panoramas, you can aggregate their information, you can do voting and resolve their conflict and so on and get better results than the individual panoramas. And that's what we do, and it actually happens. It's pretty effective. So at the end of this step, we have a mesh that is semantically segmented. For part of the data, we actually put it through manual verification too, but for a large part of it, we don't have to do it actually any manual verification. So once you have a segmented mesh, the rest of the process of constructing a scene graph is analytical because we basically know what the relationship between different edges mean, and so we can solve them programmatically. For instance, let's say a modal masks. That's what we discussed earlier, that's occlusion. So if you have a segmented mesh, you can do raycasting and extract a modal mask and construct that occlusion concept that I mentioned through a higher order edge that is object, camera, object. So if you have two objects, let's say in this case there's a toilet and there's a sink, toilet and sink are segmented in the mesh, and you know the camera parameters of where this picture is taken, so you can do raycasting and find the portion of the toilet that was occluded by the sink. So you can extract this nice detailed modal mask without having to do any kind of manual annotation or learning-based work on it. And these are more examples. These are all actually real examples from the data. And yeah, there's more of it. Basically, all the relationships, let's say a relative size, you can lay a graph over an image that tells you what objects that are visible in the scene are bigger than a reference object. Let's say in this particular image, the sofa is bigger than the smaller sofa and a bench and so on. And yeah, then all of the relationships in scene graph are then programmatically extracted after we have the segmented mesh. So here is a fly-through video of one of the meshes in Gibson database. This is Albertville. So you can see that we alternate between segmentation, between the nodes. Like I said, the mesh has registered images. So this is the image, for instance, from this particular camera viewpoint. And then you can look at the attributes for all these elements that are detected. There's a bed, there's TV, there's size of them, there's volume of them, and then these are the relation between them. What's the relative size between them? What's the relative spatial order, and so on and so forth. So now that we have the 3D scene graph for the buildings in Gibson, we can integrate it in Gibson environment. And that's what we did. What you see, let's say on top right, is the 3D scene graph channel. The relationships between different elements that the onboard camera of the robot sees are overlaid as a graph, and as the robot moves forward, you can see that the graph changes and updates and so on. So you can see that next to the conventional representations that we already had in Gibson, such as depth and surface normals and so on. So consider for a second how much more informative the 3D scene graph is for a robot compared to those conventional representations. Like suppose the robot wants to move a table while there's a cup of coffee on it. Even if you give it low-level 3D like depth, it would take millions of trials and something like reinforcement learning to realize that if you move a table when there's a cup on it, the cup is going to fall and the coffee in it is going to spill. While a graph-based representations that includes 3N semantics, it provides a type of knowledge that the node cup is being supported by the node table, so they have that kind of relationship, and it provides that information more immediately. So if you can make vision systems that can provide robots with something like the 3D scene graph, like information from the onboard camera in real time, that would be very empowering. But also I have to mention the downside, despite our advocacy for the power of graph-based representations, the example that we have here, the 3D scene graph that we have done so far, is very rigid. We have manually defined the structure of it. We have defined what are the nodes, what's the relationship between them, and so on. So it's important for future work to automatically find the construct of this graph. You can commit to a graph-based representation. They're powerful, but what would be a useful edge? What kind of information would qualify to be an edge, and what kind of information would be useful to be as a node, and so on. So it would be interesting to not have to do everything in terms of the definitions manually. So next, how we can extract such complex 3D information from raw RGB images. But for a minute, let's first discuss why we emphasize on using images for this purpose. Basically, why do we want to use RGB cameras while there are other sensors out there like LiDAR and laser and structured light and so on? That's because of the fundamental advantages of RGB cameras. Let's say versus the alternatives, they're much cheaper, typically start in $20 range. They're high resolution, 1080p or 4K are pretty typical these days. They are long range, this is important. The range is basically as far as you can see, as far as light can travel. While the active sensors usually have a very small range. They're passive. This is important because they get less interfered with sun or other sources, and they're low power. And they're also fast. Hundreds of FPS is pretty typical. They're also widespread. All of us own multiple cameras on our cell phones, on our laptops, on our dash cams, and so on. So as a test, just before the talk, I went to Robot Shop and I searched for cheap cameras, and this is pretty much one that I picked randomly. This is a wide-angle camera. It provides HD images at multiple resolutions and hundreds of FPS. It can be integrated with Raspberry Pi. It's pretty small. I think it's almost as big as a fingernail. And it's just for under $20. So compare that to the alternatives that are usually several orders of magnitude more expensive than this if you want to go for something like LiDAR and so on. So basically, if you can tame images, we have a significant advantage. But obviously extracting abstract information from images is harder and puts the pressure on developing software that allows us to do that, while the 3D sensors put that on the hardware side at the cost of making it more expensive and low range and so on. That brings us to here, like, okay, how are we gonna do this? RGB cameras give us a data like this image, and you wanna go to something like these complex 3D semantics. So obviously just throwing a basic neural network encoder decoder at it is not going to work. There's so much structure on the right that it will be hard to get them to just automatically merge out of in the encoder decoder architecture. Or any basic neural network that doesn't have much structure built in it, and it would either require a large amount of data, it would just not happen. So more promising approach is going multi-layer. So basically from RGB images, we first extract a set of mid-level cues, and those mid-level cues can be later assembled to construct something like the complex 3D semantics that we want. And ideally, there would be a feedback loop from the complex 3D semantics to the earlier mid-level cues, again, to update them and so on, to create a bottom-up, top-down feedback process. So this part of this pipeline is pretty fundamental, and it's basically referred to as multitask learning because there's one sensory data in and multiple abstractions out of it. And we have been working on that for a while. So the central concept of multitask learning is the relationship between different tasks. There are different forms of relationships. Transfer learning relationships is something that we investigate in taxonomy in CVPR 18 that tells you how much knowing how to solve one problem, how much does that facilitate solving another problem. Competition and cooperation among tasks, or negative transfer, is something else in ICML 2020. You can look at a paper if you're interested. And consistency among tasks is something that I would look to discuss today. We recently did this paper in CVPR 2020. So what is cross-task consistency? Like I said, we are interested in extracting multiple abstractions out of one image, like 3D curvature, depth, and surface normals, and so on. So if you train a neural network independently for each of these tasks or use existing multitask learning methods, The output of these tasks do not have to be consistent with each other. For instance, if you look at in the zoomed in windows for surface normals and depth, you can see that they clearly have recovered different 3D structure. What we did here was we developed a general method for learning with cross-task consistency. In this particular example, if you look at the same area, you can see that not only the results just got better, we recovered more fine-grained details, became more accurate, but also if you look at this particular pixel, in these different output domains, they're more likely to be consistent with each other as opposed to the baseline learning. So the advantages of cross-task learning, before I describe the method to you, first, you'll generally get more accurate results. You fit the data better. The generalization of the models, we noticed, improved too. And naturally, they get more consistent. That's directly built into the objective of the system. And also, there's an informative quantity that we can define based on cross-task consistency. It's called consistency energy. It's an unsupervised and intrinsic quantity that I'll actually describe shortly. So a little bit about the method. It's a fully computational method. It doesn't require prior knowledge of task relationships, or it doesn't require them to be differentiable. There's a way to get around them. So to convey the high-level idea to you, consider this elementary example. Imagine X is the input domain, and you're interested in predicting Y1 and Y2. So standard learning would train a neural network F for projecting X onto Y1, and similarly another neural network for going from X to Y2. So what we do here is that we introduce an additional edge here, H, that checks Y1 against Y2. Basically, that means you go from X to Y1, and then from Y1 using H, you go to Y2, and you check that against the direct prediction of Y2 that comes from G. Basically, you go from X to Y2 from the upper part of a triangle or the lower part of a triangle, and you check those against each other. And that they have to be the same. And that is exactly just a loss term that we add to the grand loss. So function H basically makes sure that the predictions of Y1 is consistent with Y2. So here you can see that using an intuitive example. Let's say X was the RGB image, Y1 is depth, and Y2 is surface normals. So in the upper row, if you learn to predict depth independent of normals, then projected onto normals, you can see that a lot of artifacts appear, despite the fact that depth looks reasonable, but there's just a lot of artifacts that reveal only when you look at surface normals because about the fine-grained details of depth. But in the lower row, if you learn depth subject to cross-task consistency with normals, so not only the normals improve, you can see that those artifacts mostly are gone, but also the depth itself is improved. If you look at the fine-grained details, you can see that the difference is actually obvious. So now this was about an elementary case. This is about a triangle because it only operates over 3 domains. If you have a larger dictionary of multitask that you're interested in predicting, you end up with something like this. You end up with a graph. And the first thing that you can do is that you can extend the triangle concept to a path concept. So here, instead of going from X to Y2 using an upper part of triangle or a lower part of triangle, you can do that via the blue path or the green path. And the result of both of them should be the same. So basically, you turn the triangle into longer paths. And then the state of global consistency for a graph, we define it as satisfying the consistency constraints for all feasible paths in the graph. And in the paper, we have a tractable training schedule for it because obviously training for this objective directly is not going to be tractable. And here's the consistency energy. Energy basically quantifies the leftover inconsistency in the system. So if you go from X to Y2 using the upper part of triangle and lower part of triangle, and you compare the two, if they are pretty consistent with each other, that means that the amount of leftover inconsistency in the system is low and the energy is low, and vice versa. So that's actually a pretty informative quantity that I'll shortly show what it tells you about the intrinsics of the system. So here are some visualizations. The upper row shows if you go from the input frame to some middle domain, let's say curvature or depth or shading, and then from there you go to surface normals. And this is for baseline learning. You can see that the normals are not the same. And this is the manifestation of the amount of inconsistency that existed in those middle domains as far as surface normals was concerned. And in the lower row, the same exact thing is shown, except that the learning was using cross-task consistency with normals. And I can see that the normals end up being the same. So this is, again, for a triangle, extend that to many domains. So we make the middle domains consistent with all other domains if you can solve this for a full graph. This is another way of seeing the same results. Here you go from RGB to depth and then project depth onto the alternative domains. The lower row shows that without learning with cross-task consistency, and the upper row shows it with consistency. And again, pay attention to the Y domains. And you can see that the 5 Y domains, you can see that the results improve significantly in terms of those that you project onto, but also the depth itself improves. So if you pay attention to the fine-grained details, you can see that the depth with cross-task consistency actually recovers more fine-grained details and so on. All right, this is also an important practical point. So this idea is not useful just for multitask learning, but also single-task learning. So here's a simple trick that you can use. Let's say if you're interested in predicting some Y1 domain given X, instead of training a network to do just X to Y1, that's what we typically do, train it to do X to Y1 to Y2, using the method that we describe in the paper. You will actually end up with better results for your Y1 prediction, because Y1 to Y2 acts as an additional loss for you, something beyond the standard loss that you use. It projects it then to another domain and also makes sure that the prediction that you have for Y1 is consistent with that, besides the existing losses that you have. And the question is then what you can use as Y2. Even if you don't have this multitask data set, all you have is annotations for Y1 on X images, you can still do this. You can basically make up Y2 domains. That's something that they report in the paper. For instance, you can find some unsupervised domains like texture edges or 2D key points. These are domains for which we have programmatic solutions. Given an image, you can apply, say, canny edge operator and then extract the texture edges. And you can use that as the Y2 domain. And interestingly, you can see that the results of surface normals prediction actually improve. That's what you see in the middle row here. So this is really interesting because it shows that you can use this idea for single task learning as well, not just multitask learning. So we did the experiments on a number of data sets, and we have a number of baselines too. Most importantly, we have obviously standard independent learning and multitask learning. A standard multitask learning basically uses a shared encoder for multiple output predictions. We showed that that's not actually sufficient for getting cross-task consistent predictions. Cycle-based consistency is a very common form of consistency. It assumes a bijection between domain X and Y and more. So first, some results. You can see that generally the results of learning with cross-task consistencies is better than not using the consistency constraints. If you pay attention to the fine-grained details in the yellow marker, you can see that there's a lot more details recovered by cross-task consistency. And here is the energy. The higher the energy, the intensity of the pixels increases. For instance, let's say look at the lamp. There was an area of high uncertainty there, high energy, because I guess the pixels within lamp are saturated, so it's unclear what the 3D in there would be. So naturally that led to a high uncertainty over there. And similarly, let's say where the counter meets the floor, because of color similarity, it's unclear where the counter ends and floor begins. So that led to also high energy. That means that different paths led to different results, so it was uncertain what exactly the final prediction should be. We can see the same here over video. For normal prediction, reshading prediction depth, the video actually shows fine-grained details a little better. You can also see these videos on our website, so I'm going to skip them in the interest of time. So here are predictions on data that is far from our training domain. So this is a painting by Van Gogh. This is a Cotton Mill Girl. It's a grayscale popular image. And more. So these are far from the training distribution, but the networks held up pretty well. That says they generalize pretty well. There's actually a live demo you can visit. If you go to consistency.epfl.ch demo, you can take a picture with your cell phone and get the results of predictions from different networks. We also have a demo in ECCV on Thursday. And here you can see the comparison with baselines. The story remains the same. If you use the cross-task consistency constraints in learning, you'll end up fitting the data better and generally improved results. You can reproduce the same comparison on the demo page as well. And here's the same thing again shown on video frames. Like I said, the video frames, this is a frame-by-frame prediction, so there's no temporal smoothness. Still, we can see that the fine-grained details are covered, and they're actually pretty consistent across different frames. And finally, here are some utilities of consistency energy. First, this plot shows energy over the course of training. You can see that energy for cross-task consistency significantly drops throughout the course of training, while that's not the case for baseline independent learning or multitask learning. This is important because it shows that when you compare this with multitask learning, standard multitask learning, just having a shared backbone is not enough for organically getting cross-task consistent results. You really need to explicitly constrain your model to be cross-task consistent. Here you can see the correlation between supervised error and energy. There's actually a good linear correlation between them, 0.67. That means that if you just look at the energy value for a particular image, you'll have a good idea if the results are wrong or not. So I can use this as a confidence metric, and it's important because the energy is completely unsupervised. You can extract it on the fly for any data. And these show the correlation between energy and domain shift. So continuous domain shift or discrete domain shift. You can see that as you go more out of distribution compared to your training distribution, the energy increases. So again, the energy is a good indicator of whether you're going out of your training distribution. Potentially errors might appear in your predictions. Okay, and finally some words on how to use this information to extract it for downstream purposes. So far what we discussed was how, given an image, we can extract multiple visual cues out of it. But vision is usually a service in support of some downstream goals. So we need to relate these visual abstractions to downstream goals. And if the downstream goal is a robotic task, the pipeline looks like something like that. The output of visual perception module goes into a control module, and that control module issues actions that goes to the hardware of the agent, and the agent executes that, and this loop continues until some downstream goal is satisfied, like a door is opened, or object is moved or manipulated, and so on. So to give you an idea about the type of downstream task that we're talking about, like navigation is a good candidate. You task the agent to go from one particular point in a building to another particular point. And that's something that we worked on in 2018 and 19. And more recently, we have started working on visual manipulation. You have an object, you want to push it, you want to pick and place it, and so on. So the setup of this integration is actually pretty simple. You get a visual observation from the camera, using the pre-trained networks to extract the mid-level representation, and that's what goes to the policy, reinforcement learning policy that extracts the action from it. And we compare that with this tabula rasa or scratch learning. That means pixels directly go to the policy without having to go through the mid-level abstraction. So that's tabula rasa because that means clean slate learning. The pixels directly go to the policy, so the policy does not have any kind of priors about the visual world, about the world visually. While on the left, the mid-level representations, you can think of them as some priors that you provide your model in terms of the world visually, like the world is visually 3D, and then there's like segments in the scene, and so on and so forth. And we compare the two in terms of whether learning with these visual priors accelerate learning or they generalize better or not. So I'm going to show you just qualitative results. The answer to both questions is yes, and I'll let you see the paper for quantitative analysis. Here the task was identifying a target and going to the target. You can see that when you learn with perceptual priors, the execution is pretty smooth. The agent finds the crate as soon as it sees the crate, which is a target object here, it navigates to it. While if you do that without these visual priors, the agent frequently gets stuck. It cannot complete the task very often. By the way, all of these, there's a hard separation between train and test here. We train these policies in one building and test them in a completely unseen building. So the generalization is actually important. This is another task. This is maximum coverage visual exploration. The agent is supposed to travel as far as it can in the shortest period of time. The story is the same. If you do use visual priors, you do much better than not doing so. And similarly, this is local planning or point navigation, going from one arbitrary point in the building to another arbitrary point in the building. If you go to actually this website, you can select the downstream navigation task that you're interested in and select from a broad set of 2D or 3D visual cues and see how they compare. It's a good way of actually getting some hands-on experience and some intuition about how these models work. So like I said, I'm not gonna show you quantitative analysis, but there's one thing that is important, is that using these visual cues is not only beneficial but also critical. So here you can see that the performance of train and test, these are the rewards. So the red curve shows the reward during training in the training space, and blue shows that for test space, and the dashed line shows blind agent. That's a control baseline that quantifies how an agent that is aware of the structure of the building and so on, but doesn't see any visual information, how it would do. You can see that blue in the test building collapsed to the performance of that blind agent. It means not much visually transferred from the policy that was trained in the training building to the test building. And the story remains the same for the other task as well. But when you look at these curves using visual priors, they actually remain high, remain close to the training set, which means using the visual priors actually help you with generalization. So we did the same experiments for visual manipulation too. Here you can see the generalization experiments. The setup is pretty similar, except that the task, instead of being navigation, is manipulation. So at test time, we surprise the policy with new textures or new objects and so on. You can see that with visual priors, the mid-level representations, they cope very well. While not using them, the policy collapses, and also domain randomization doesn't work very well in this case. In the paper, actually, we have a discussion how domain randomization is related to mid-level representations. Both of them actually provide invariances. One of them does it at the level of vision and in an asynchronous way, while domain randomization does it at the level of the end-to-end policy and synchronous with learning the control and so on. So see the paper if you're interested in how the two are related. And finally, we can do another generalization test, this time to the real world. Previously, the generalization was to novel objects or textures, but we can do the same with the real world. You train the policy in simulator and test it in real world and you see how well it generalizes. So it does actually work reasonably well when you use the mid-level priors. Here's an execution. This is completely trained in Gibson. It has never seen the real world, but you can see that it still recognizes the objects. It doesn't run into the wall and so on and so forth. And finally, these are some material that I didn't get to talk about. First, we have a demo of cross-task consistency on Thursday. Like I mentioned, feel free to drop by. If you're interested in the incremental aspect of multitask learning, you can see the site tuning spotlight. I believe that's also on Thursday. And also, if you're interested in the negative transfer aspect between different tasks, that leads to the question of grouping, which tasks that you should group together when you're trying to do multitask learning. I didn't discuss that too. We recently presented that in ICML last month, but the presentation material is online. Feel free to look at it. And for reference, these are the papers that are referred to throughout the talk. Thank you very much for listening.